Yes, yes.
Good morning, everyone. My name is Jeffrey Mark Ivinson of 112006232.
Okay.
Today we're going to be talking about Indiana Jones. So I'm going to give a brief introduction about Indiana Jones. It's about an archaeologist going on adventures. So these are the scenes that we are going to be talking about, and I'm going to start off with the falling off a truck scene. So let's watch the video from 4 minutes 30 seconds. I took this from the 1981 movie. There's a sequel, but there's a rerun, but I'm taking the older one. Okay. So in the scene, Indiana Jones are running away from the soldiers because he stole an artifact from, I can't say the name, but it's Nazi. And in this scene, a soldier fell down backwards instead of, I'm going to be explaining about it a little further. So what went wrong here? So let's assume that the vehicle is moving at around 50 to 60 kilometers per hour. And we saw in just now that the soldier fell backwards. So what was wrong with that? So when he actually fell backwards, I'll say it breaks the laws of physics. Because in actual physics, if he would have actually fallen, he would have actually fallen towards the same direction as where the truck is going. So in this case, being to the left. So in here we can follow Newton's first law, or law of inertia. Next. So let's narrow down the vehicle speed to 50 kilometers per hour to make it a lot easier. So if the vehicle is moving at 50 kilometers per hour and the soldier is not moving just now, we'll assume that the initial velocity of the soldier is also 50 kilometers per hour. So following that, using Newton's first law of inertia, unless acted upon an external force, or let's say a tree just now, object remains at rest, and if it's in motion, it moves in a straight line, meaning it also moves with the vehicle. Mm-hmm. That is it for me.
Okay. Can you calculate what happened to him? So he's moving like 50. Can you
50.
reproduce what is actually like that?
Sorry?
Reproduce what the scene should look like.
So if...
in your home.
Oh, okay.
Okay. Okay, good. Jerry.
Right. Good. Is this working? Yeah. Okay. Good morning. My name is Kai Goto. I'm 112006205. So the story is about rescuing enslaved children from a cult in India after they steal sacred stones. And the movie is Indiana Jones and the Temple of Doom, which is a different series. It's the same series, but different year from the previous one. Okay, can you play the video? It's unplayable. Just go to YouTube. 49. Okay. Okay. What did you touch? What did you touch, bro? Okay. So here's the scene. This scene right here. Okay, you can stop. You can go back. Okay. No, just go back. Okay. Next. Okay, so let's break down the scene first. There's two adults in a cart and one kid. One of them is a guy, and one of them is a woman. They're in a metal minecart, and the minecart is moving forward in a relatively high speed. And it is going through a sharply carved railway track made out of metal right there. And there was no depiction of using any brake usage.
Okay.
There's a brake in front of the cart, but they didn't use it at all. Yes, let's go to the next. Okay, so by Newton's first and second law, the cart will remain in the track only if the frictional force is sufficient enough to provide the centripetal force required to keep the movement of the cart in a curved path.
Right.
So if the centripetal force is greater than the frictional force, then the cart would fly off the track. So in order to calculate that, we need to have centripetal force first, and then frictional force. So I made some assumptions based on the movie, where the minecart weighs around 500 kilograms. Indiana Jones, who is muscular, weighs about 85 kilograms. Willie the Scott, the lady, weighs about 60 kilograms, and the kid, short round, weighs about 30 kilograms.
Sorry. Okay.
Can I continue? And the velocity,
Stuart, right?
yes, and the velocity is assumed to be 15 meter per second because it's relatively high, but the average speed of the minecart is about 8 meter per second. And the radius of the curve is about 8 meters, and the gravitational force is constant, which is 9.81 meter per second, and coefficient of friction of rusted steel is about 0.65. So
How do you know 8 meters?
8 meter, I just approximated using Indiana Jones' height, because he's about 1.85 and he didn't fit completely in the cart. And when I tried to align the cart with the curve, it was about 4 times Indiana Jones' height.
Okay.
So the total mass,
The coefficient friction.
yes, it's
Do you consider it's a railway? Because the railway has this thing sticking out, right? It's not just the metal on metal. It has a sticking part to hold it, right?
yes, but
Like a wheel of the train is like this, right?
yes,
So
yes.
that it doesn't go out.
Yes, I was thinking of that as a one factor, but in order to simplify the calculation, I didn't consider it in this part.
Fine for now. Okay.
So total mass, you just added, it's total of 675 kilograms.
Right.
Centripetal force, if you put it in the equation, you'll get 18,984.38 newtons. And frictional force is about 4,304.14 newtons. So when you compare these two values, it is obvious that centripetal force is way greater than the frictional force.
Okay.
And if you could look at that right bottom corner, so it matches the right box, which is frictional force is smaller than centripetal force. So the cart would, of course, fly off the track. But in the scene itself, the cart was still enduring
Right.
and made it back to its track. So this is considered as a flaw in the physics. And I think that is it for me. And here's the scientific term. Centripetal force is a force that is always directed toward the center of the circular motion, and its magnitude is constant.
Okay, very good discussion. But you know where the homework is coming, right? So please consider this rail,
the-
shape of the rail, and then see if that's going to change mu in this case. You can just look up what's the mu in a real train.
Are you,
See if this is going to hold or not.
are you talking about the one in the wheel that sticks out?
Yeah, the wheel is something like this, right?
Yes.
So the mu must be larger.
Yes.
It's
Okay.
larger than 0.6, I think. So
Okay.
can you look it up?
Yes, I will try
Okay.
to.
And then also, they should move. So when you, so first of all, when they design these kind of things, they design it so that it doesn't fly away. No,
For the actor's safety, I guess, but if
yeah, accessibility, but in reality,
yes.
design rail, you design it so that trains can fly away, right?
Yes, but in this case, I believe that the cart was going way off the speed of the
That's true. Yeah.
the
that
things,
should be,
so they should be very slow in the actual usage, but they made it into 15, so
fair enough. But
it's
then
kind of like
they shoot the movie scene, right? They shoot the movie scene, right? In the movie,
yes.
they shot it, right? And then they shot it. The car is running, right?
Yes.
With the front, right?
Yes.
So there must be. So how did they shoot it? If this is correct?
Oh,
If this is correct,
if
even in the movie when they are shooting, it should fly away, right?
yes, and
So can you look it up how they shoot it?
in the homework or
Yeah, I mean you can look it up how they shoot the movie.
okay, yes,
Like behind the scenes.
yes. I will try to look for it.
But I like the argument. It was very good.
Thank you so
Okay.
much. Next.
Next, Darren.
Hello. So hello, my name is
Right.
hello, my name is Darren, and I'll be explaining one of the Indiana Jones scenes where they, Temple of Doom, where they escape from a plane using a lifeboat raft.
Okay.
So here how the scenes goes.
Can you speak up louder, voice?
Okay. Hold on. It's this part. Oh, no. So yeah, as you can see, they run out of parachutes because previously the pilots have taken the parachutes and they're about to crash because the fuels are running out. And they crash, prepare prepare lifeboats, and through the tight entrance, they fall out. Should be in any seconds right now.
They jump out of the plane?
They jump inside of the raft, and they consist of 3 persons. As you can see, like, oh yeah. So here's the fall, and in the shot they use dummy scenes because it's not realistic, and they managed to safely fall without any injuries.
Miracle.
Yeah. So yeah.
Okay.
Okay, stop. So I'll break down the scenes. So to find out if they managed to survive the fall or not, I used Newton's law and found out, in this case, I used terminal velocities to find the maximum speed they could achieve during the free fall, and also once the speed they'll be reaching to the ground. And so then the terminal velocity will be compared to the statistics of mortality rate of falling, which I'll found in some articles, and also the fact of falling in certain heights. And in this case, okay. So here how the calculations goes. So I use the terminal velocity formulas, which is Vt equals to root of 2 times mass times gravity out of air densities and the area of draft, and also drag coefficients. So the data I gathered, first I'll accumulate all the mass. The Indiana Jones, Willie Scott, the girl, and the child actors, and also draft, right?
The body weight very accurate.
Yeah, because I found it, and for the child, I'll just approximate the weight of the child. So for the air densities, instead of using the sea level air densities, I use the cruising altitude, the typical cruising altitude densities, which 0.364, or sometimes it shows like 3037, but like in this case I use 364. So for the surface areas, I also found it in Google through eBay. So the lifeboat they're using is approximately 7 meters squared in surface areas, and the drag coefficients I found it in the internet also. So once I plug in all the numbers, then I'll get approximately 4.994 meter per second, which is really fast. And to know how fast it is, I converted it into the miles per hour, which is approximately 101 miles per hour. And
Miles per hour.
yeah, so the human body can withstand across.
You do this calculation by yourself, or you copy from website?
Oh no, I used the formula from someone else, but like it's not correct, especially the densities and also the mass. So and then once I found the miles per hour, I found out that the human body can withstand across 120 miles per hour while falling in the like laying down, and so they might not survive. Well, no, like there's a high chance they might not survive. That's what I'm trying to say. So then I'll convert the velocities to height to know like how tall they were falling off. So I use the standard formula of velocity, which is V equals to root of 2 times gravity times the height. Then I rearranged the stuff. And then I found out they were falling from 127.24 meters high, which is really tall. To compare how tall it is, the Pyramid of Giza is 130 meters tall. So yeah, that's approximately how tall they were falling. So next.
I think terminal velocity, so you calculate the height to reach terminal velocity,
Yes.
but how do you know it reached terminal velocity? It might be still accelerating, no?
Well, it's hard to know because the scene itself, it's shot using like dummy and it's really far. So Don't know.
I don't think you can guess the height from terminal velocity because we don't know if it's at the terminal velocity or not.
Oh no. Okay. So yeah, let's assume they were falling from this type of height.
Assume? Okay,
Okay.
sure.
And it's quite deadly because so I found out one of the articles. It's called "Falling from Heights," like analysis or statistics they gathered on
Just into the paper.
on whether they will survive on certain heights or not, and like what effects they will bring. So it shows that falling from 18 meters above is guaranteed to have like 50 to 100% fatality rate, and in our case, it's way beyond the 18 meters cap. And also, I've compared the relationship between trauma scores and also fall height. And so, from the table, you can see that above 9 meters, they will have like these, I guess, trauma scores to measure how much trauma they can receive from the accidents. So I'll be explaining some of the notable variables, such as GC, which is Glasgow Coma scores, which conveys the level of brain injuries during a fall. And so it shows that it has 11, so suggests that it might have moderate to severe injuries. And the ISS, yeah, so it's deadly. So in conclusions, Indiana Jones have small chance of surviving, but they won't survive without any injuries. It's impossible. So they'll fall with some certain injuries, as shown here.
Okay, so this is just head-on collision. Assuming that you fall from hit a hard ground, right?
Yeah.
But then here, they land on a snow slope, and they keep going, right? They just land on snow and then they keep going, right?
Yeah.
So the shock
Once
will
they.
be reduced because you are not stopping there, right? You just go like this, right?
Yeah.
So can you consider and then reconsider?
So okay.
And also the height you should measure from the movie, right?
Oh, it's not sure.
You should first you measure the height from the movie and then calculate the velocity. That's the order, I think. Okay. And then if you still find, so please fix these two. And if you find still they're going to die, try to calculate how much larger what's the boat?
Oh, the raft.
Yeah. If the raft is larger, can they survive? They can.
Oh, well, there's supposed to be one sections where they use hypothetically they use the raft as a parachutes, which Mythbuster did, and they might survive. So, okay.
Okay, if it's large enough, they can survive.
Yeah.
So try to find it.
Okay.
But a very good report. I like that.
Thank you.
Thank you, guys.
Okay, hello everyone, my name is Samuel, 112006225, and my title for this presentation is Can Your Fridge Be Your Shield from a Nuclear Bomb? What's next?
Fridge. Okay.
One, 1, 2, 3.
So Indiana Jones is going to hide in a fridge?
Yeah, as you can see in the movie, so there's a nuclear
Goes
bomb.
inside?
Yeah, he squeezed himself.
Oh, so scary.
Okay, stop. Okay, as you can, next. And also before that, I want to tell you about the director of the movie, George Lucas. He claims that he already consulted with scientists and say that India actually have a 50-50 chance of surviving the situation. So now we will do some computation. Is it true or not? And also a small reminder that Indy not just use any regular fridge, he uses a lead-lined fridge. And also, as you can see in the movie, he doesn't suffer any visible injuries after the incident. And also in this presentation, I will focus on to explore the plausibility of Indiana being able to survive this event by investigating how thick the lid within the fridge would need to be.
Interesting.
So let's make an initial assumption since I don't know how is the far away from the bomb and the fridge, so I assume that is 1 kilometer. And also the surface area, because as you can see, Indy can squeeze himself into the fridge. So I assuming it's 1.7 tall and 0.6 wide.
Okay.
So to get also a good number of surface area. And also the gamma radiation is spherically isotropic. And I assume that loss in energy due to absorption from air and the house is considered negligible.
Fine.
And also, let's start with the fraction of gamma rays. So we have to use the solid angle formula and divide it by 4 pi. So solid angle is equals A over 4 pi r squared. You just need to input those number 1 and 1 kilometer. You will get the solid angle 7.9 times 10 to the minus of 8.
Fine.
Then also because in the movie we didn't know which type of bomb he used, so but it takes place in 1957. In 1957 also have an Operation Plum Bomb, and so I just take 3 as an example: Boltzmann, Smokey, and Hood with Boltzmann 12 kilotons, Smokey 44 kilotons, and Hood 74 kilotons.
Okay.
And so we need to count the energy. So 1 kiloton is equals 4.184 terajoules. So we just need to times it, 12 kilotons for Boltzmann, and you get those results, Smokey and Hood. What's next? Now we need to count the gamma energy. And from the research paper I found, it says that about 5% of the energy released in a nuclear airburst is transmitted in the form of initial neutron and gamma radiation. So from the energy of the bomb, it's not all is transmitted into the gamma radiation, only around 5% of them. So we need to find the energy of the gamma radiation, 5% of the bomb.
Right.
And also the energy reshift by the fridge. The gamma radiation reshift by the fridge is the energy of the gamma times the solid angle of the fridge. So these are some numbers that you can counting, and you got this result for Boltzmann, Smokey, and Hood. What's next? Now the radiation absorption. So this is the formula: I equals I naught e to the minus mu t, where I is the energy of gamma radiation at thickness t, and the t is the thickness we need to find, and I naught is the energy gamma radiation to the fridge. So it's based on the bomb. If can you go back a bit? So if it's, for example, Boltzmann, so the I naught is 1.9 something here.
Okay.
And how about the mu? Mu is because we're using lead lined fridge. So from, if you can see at the right hand side, the density of the lead is 11.3 times 10 to the power 10 cube. That's in kilogram meter cube. So you need to change it into gram centimeter cube. And also you can see we approximate the mass absorption coefficient is around 0.1. So we just need to times both of this to get the mu of lead.
This is for the lead, right?
Wait, go back. Huh?
This graph is for the lead.
Yeah.
Okay,
Go back. Okay, next. And also we need to know what's the maximum dose gamma radiation to human. So based on Google, it said that around 0.5 until 1 gray unit. And also we assume that Indiana is strong, so he can hold until 1 gray unit.
Okay.
And 1 gray unit is 1 joule over kilogram. So it means that Indiana, let's assume he's 90 kilogram. So the I is 90 joules.
Okay.
Please. So we already get the I, this 90 joules. We already get the I naught based on the bomb. We already get the mu, and we need just finally to find the thickness. So you just do some computation here, and you can get the, so you need at least like 6.77 centimeter thick of lead for the Boltzmann bomb. And you have to note that this is 1 kilometer away from the bomb.
Right.
So if, for example, you need 2 kilometers away or maybe further, you will have a different result. So next. And also a fun fact that your fridge at home is not lead lined.
Right.
So don't try this at home. So that is because lead is a metal and metal conducts heat. And no household refrigerator will have a thick line of lead when it tries to insulate the heat from the outside. And also that your fridge at home is mostly used polyurethane foam. And here are some references that I use, and that's all from my presentation. Thank you.
Excellent. Very good. Very good. Okay. Very good. Very good.
Okay, good morning. My name is Matthew Wilbur, and I'm going to continue. The scene from where some have left us is where the Indiana Jones surviving the lead-lined fridge launching with a speed of up to 120 kilometers per hour, which is the speed that overpays the car running in full speed. And I'm going to prove that he's not gonna survive that.
So this is the same scene.
Yeah.
Yes.
Okay.
Masih awal banget.
Yes. So here's the part where the nuclear bomb starts to explode. Then there's the Soviet car, which is the 1950 Ford Deluxe, is running with full speed, and then just the refrigerator just launch and then overpace them. And then in this scene, we can see that Indiana Jones,
He's inside?
yeah, he's inside there,
Oh, no.
and he is not even experiencing any trauma or any broken bones.
That's so strong.
So in my hypothesis that in this scene, the nuclear, maybe the lead line fridge can protect Indiana Jones from the nuclear explosion or the rays or the radiation, but he's not going to be protected from the force or the impact he's going to suffer or experience when landing, or even from blasting out of the site. So that he will face any suffocation or be crushed from many sides because the fridge is small, and maybe the intense heat next. So for my assumption, I'm going to use the place and time which Sam has given, which is the Operation Plum Bob, which is considered as a tower drop, and I'm going to use the power of the bomb to be the middle, which is 44 kilotons. It's from 10 to 74, so I'm going to use 44. So next, I'm going to assume the fridge weight. I'm going to pick this type of fridge, which has that dimension in inch. So if we calculate 2 meters, the width, the depth will be 0.76 meters or 0.7 without the door and the handles, and then the height will be 1.5 or 1.5 and below meters. And then I'm going to consider Indiana Jones to be 99 kilograms to make the total weight 170, like it's easier to count. And the car is shown here. It's the 1950 Ford Deluxe, which theoretically has the top speed of 40 meters per second, which is up to 120 kilometers per hour. And because they're running from the chaotic event, which is maybe they're not going to use their top speed because it's going to be very dangerous for the Soviet. So I'm going to assume that they're going to be in the middle, which is 35.76 meters per second, which is realistically at a high pace for 1950 car.
Okay.
So the estimation will be in the movie we can see that the distance from the fridge and from the car is 2.3 meters, and then from the scene we can count that it overtakes the car in 0.9 seconds, which is very ridiculous. And note, we haven't counted the vertical velocity or the acceleration, because the displacement of the vertical displacement or the magnitude of displacement is difficult to really see or to measure in the scene, and so we must consider this as lower estimates. Because why am I using lower estimates? Because lower estimates has already proven that Indiana will not survive this event. So next we'll count the impulse and momentum change. What is happening? So we're gonna ignore the drag and wind resistance because they're too hard to calculate in these chaotic conditions, and because we're considering lower estimates here. So the momentum change will be the fridge mass and plus the human mass times the velocity that we have counted before. So we can compare this to the bombs dropped on Hiroshima and Nagasaki, which generated winds up to 620 miles per hour, which is 277 meters per second. This is not the power of this bomb, of the Hiroshima and Nagasaki bomb, is not even the bomb of the Operation Palm Bomb is 5 times bigger. The power of the bomb is 5 times larger than the bomb dropped in Hiroshima and Nagasaki. So yeah, it's considered as lower estimates, but it doesn't matter. So even from 1.6 kilometer away from the explosion, time for the wind to pass through the fridge, which has the depth of 0.7, as I mentioned before, it's going to be 2.5 milliseconds, which has the force of impact on the fridge and the human to be 6. The impulse divided by the time, which is 2.6. Again,
We still have Nicholas, right?
So why it doesn't work? Because the fridge is moved as fast as shown in the calculations, and so the placement of the bomb is supposed to be closer. And from the slides we skipped, I've shown the calculations on for the placement of the bomb, because we don't know. So the placement of the bomb is supposed to be 0.6 kilometers from the Dolan's nuclear knowledge. So the close placement in the fridge is going to be, the close placement is going to affect the fridge by making it destroyed due to heat, radiation, and blast. So surviving an atomic blast inside the fridge is extremely impossible or unrealistic.
Sorry, I didn't understand. Why did you come to this conclusion?
What?
Can you show the number? Why did you came to this conclusion?
Because based on the Dolan's, I found the formula to be, I've counted the formula is supposed to be, the distance is equal to the yield of the.
Can you show in one sentence?
Oh yeah, the distance is equals to the yield of the bomb, which is, I used the 44 kilotons to the power of 1/3, and times the proportionality constant, which is marked as.
I don't understand. Please explain more thoroughly in the report. I don't understand at all. Let's go to Nicholas.
Thank you.
Okay, hello, my name is Nicholas Teo, 112000270. I'm here to talk about the rocket sled scene from the movie Indiana Jones of the Kingdom of the Crystal Skull. Okay, let's go. You can skip the 10 seconds. Thank you. Okay. So as you can see, the rocket blasts away. Now there are two people, Indiana Jones and the soldier. And from here, I'm going to explain why they are not supposed to survive or even survive without an injury. And it is pretty much fatal for an ordinary person. Okay, since this movie is based on 1957, I'm going to take the closest one, and it's probably referencing to this person called Colonel John Staub, where he reached 46 Gs, the highest record known to men to have withstood it. Okay, next. Okay, so the speed it says in the report that I read was 620 miles per hour or 277 meters per second. And from Newton's third law, I'm just going to explain exhaust gas propulsion, in which so imagine the gas, like the fuel, gets burnt up and it will push the gas away, and because of that there was an opposite reaction and it will push the rocket away. And remember, the important part
is that they have no safety gear, and Indiana Jones is probably just a scholar or the archaeologist. Okay, next.
So where did you get this speed?
Huh? The speed? It is said to be. I just checked in Google. It says that they reach. It is based on Colonel John Stopp.
Okay, this is Colonel speed.
Yeah, this is Colonel speed. So I just take it as based on the latest technology. Okay. Oh yeah. Okay, so first thing first is that they were withstanding 32,900 newtons of energy. Right? First, let's talk about the calculation. Air density, you know, max speed, we already have it. Cross-sectional area of a human in a seated position, it can even be lower, like 0.6, but, because they were sitting straight, not just like this. Okay, then drag coefficient of average sitting human. I tried to check it, the information from Google or even ChatGPT because I was confused. It can be 0.75 or even 1, but to make it simple, I'm just going to make it 1. Then after the calculation, I get the drag force of 32,900 newtons of energy, and and you have to and they were withstanding it without any safety gear. So it has to hurt like hell, or even your rib cage to cave in. Okay, next.
What about Colonel? This Colonel was the same situation?
The colonel, he had some broken ribs and a lot of damages, but I'll talk about it later. And he was, and this calculation is actually like the toned down version, you know. Okay, in the so this is what I meant by toned down version. Instead of 0.1 second or 0.5 second, or it's not supposed to be 0 meter per second, but let's just say it like that to make the calculation simpler or easier to understand. Okay, so imagine the acceleration of 277 meter per second square. So that you can imagine the impact force, how much it will hurt. Okay, next. Okay, so 1 g-force is like 1 Earth gravity, right? So imagine they were withstanding 28.3 g-force. And remember, this is the toned down version. They probably withstood like 45 g-force or 46 g-force. It was not like what Colonel John Stopp did. Okay, so the usual limit that I Googled was 9 Gs, usual human can withstood. But that's for average human. For pilots of the such, probably much higher. But they were not pilots. They are not pilots. Remember that. And a lot of potential injuries that they could experience that I checked from Colonel John Stopp is first concussions, because the amount of speed you will have. Imagine sudden stopping and sudden starting, like rapid acceleration, deceleration. It will hurt your brain. Temporary blindness, because the amount of ocular pressure, like the pressure on your eye. Okay, let's just go next. Everyone understand this. Okay, the impact force. This is one of the things that don't make sense. Let's assume his weight will be 70 kilograms, in which the average human male weight. Velocity 277 meters per second. Time is 1 second. This might be okay. So anyways. So this is the calculation of the formula, and the impact force of stopping is 19,390 newtons. This amount of force, without seat belt, without safety gear, will throw you in front away. But the fact that they were still here does not make sense. And the conclusion is that they were supposed to be either dead or suffer very bad injuries, like critical injuries. That's all I have. Okay. Thank you.
Good. But then how do you know it stopped in 1 second?
No, I'm assuming it's not supposed to stop in 1 second, like 4 seconds or 3 seconds, but I'm just assuming because, like, it's supposed to have so much more supposed to be 0.5. Okay.
Can you calculate how many seconds then they can suffer?
Oh, sure.
If they can slow down slowly, taking longer time, the force will be smaller, right?
Yeah, but this, okay. Don't worry.
Very good, Nicholas.
Okay, thank you.
Yep.
So here's the Kahoot codes. Read code, scan the QR codes. The questions will be easy.
I'm not sure my laptop is doing good, but okay. I mean,
So, okay, let's go. First question is, to maintain stability in the raft, these are my scenes. They need to distribute their something evenly, like to maintain the center of gravity. Yeah. Second question is, a minecart moves along a flat, non-bank curved track to constant speed. So what force keeps it on a circular path? Third question is, Newton's first law, law of inertia, states an object stays at rest or in uniform motion unless forces acted upon by So these are the last questions. A rocket sled accelerates rapidly along a straight line. So which force are acting up in the scenes? Okay.
who got first prize?
Say, oh, Justin.
Just
Justin, that's
you can tell from that. Okay. Okay. Okay.
okay.
Good. Okay. Thank you very much for your presentation. Yeah. Please make
Thank
sure
you.
to come in your phone. Thank you all of you. So see you next time. Yeah.